The efficiency of a simple machine is an important measurement, and the efficiency is equal to the work output compared to the amount of work input. So we would hope that the outcome for our effort is large in comparison to what we have to put in. Let me illustrate this with an example of a third type of simple machine. We've already seen inclined planes and pulleys. Here let's investigate the third type, known as a lever. So again, we could use this to lift our 360 Newton object a distance of 5 meters. So if we push down here, however hard we push would be our effort force, Fe, and we know the weight of the block is our resistive force. And when we push down, then the lever is going to take on this orientation. Let's fix that. Okay. Oops. Let's clean this up. Try again. Okay, so the object ends up, we'll say, for example, lifting through a displacement or a height of 5 meters. But you could tell that the distance you push it is much greater, right? So the effort force multiplied by the distance d is the work input. The work output is the resistive force multiplied by the height, h. If this is ideal, then these quantities would be equal. And we could say, for example, exactly how much effort force do you have to apply? Well, if the work out and the work in are equal, in other words, if this is a 100% efficient machine, effort force times this larger distance is equal to the resistive force, or the weight of the object, multiplied by the height, h. So the effort force would simply be the resistive force multiplied by a ratio of h over d. So let's say, for example, by placing the fulcrum at the location we did, notice it's not at the midpoint of this beam, it's shifted farther over to guarantee that d is greater than h. So let's just make up an example in this case and say d is equal to 15 meters. Then our effort force would be equal to a weight of 360 newtons times 5 meters divided by 15 meters, which would be equal to 120 newtons. In other words, because the ratio of the height to the effort distance is 1/3, then the ratio of the effort force compared to the weight you're overcoming is also 1/3. So we define efficiencies here. We define advantages. There are two types of mechanical advantage. There's something known as the IMA. That stands for the ideal mechanical advantage. And then there's something known as the AMA, stands for the actual mechanical advantage. So mechanical advantage should be a number larger than 1, and it's an advantage that's based on the distances, or at least the ideal mechanical advantage is based on distance. So it's actually equal to the larger effort distance divided by the smaller resistive height. So in this example, we would have an IMA equal to 3, right? D compared to H is 15 compared to 5, 3 to 1. So we have an ideal mechanical advantage of 3. Now the actual mechanical advantage in this example problem, well, it also should be a number greater than 1, but it's based on force, not based on distance. So it's the resistive force, or the weight of the object, divided by the effort that had to be applied. So we overcame 360 newtons in this example, but only had to apply a force of 120 newtons. That's the trade-off. This force can be less than the weight of the object if you're willing to apply that force over a larger distance. So the AMA was also equal to 3. Now the efficiency is simply a comparison of the actual mechanical advantage divided by the ideal mechanical advantage. Well, in this case, it's 3 over 3, or 100%. But one thing we're overlooking here is there may be some friction in the mechanism that makes up the fulcrum. If that's the case, then this force wouldn't just be 120 newtons, it would be 120 newtons plus some amount to account for the friction force. So maybe in our example, we'll say that the effort force actually came out to be, how about 180 newtons of force. Then if that's the case, our actual mechanical advantage would have only been 2, not 3, and so our efficiency would have been 67%, not 100%. Now that's probably not likely for a lever. Usually levers are among the most efficient simple machines because there's not a lot of moving parts that are rubbing together. As long as the mechanism in this fulcrum doesn't have a lot of friction to it, then it's probably the case that you don't have to add much more beyond the 120 newtons to get the object to lift the 5 meters. So maybe a return to our investigation of the inclined plane. So if our plane was inclined at 30 degrees and we're trying to lift the object 5 meters, and this is still an object whose weight is equal to 360 newtons, then I think it's pretty easy to argue that this distance here would have to be 10 meters, right? That's just a consequence of a 30-degree angle. So how large is the effort force? Let's see. The work in would equal the work out in the ideal case. So the effort force times the effort distance is equal to the resistive force, which is just the weight of the object, times the height, h. So again, our effort force is equal to the resistive force times h over d, which is really a way of saying our effort force is our resistive force divided by d over h, which means it's the resistive force divided by the IMA. So it's, in this example, 360 divided by 10 over 5. So we would have an effort force of 360 divided by 2, or 180 newtons. So let's see. If we lift something directly with a force of 360 newtons straight up a distance of 5 meters, that requires 1,800 joules. If instead we apply a force of 180 newtons, instead of lifting the object straight up with a force of 360 newtons, 180 newtons over a distance of 10 meters is also 1,800 joules. So the work in of 1,800 joules matches the work out of 1,800 joules. But what if this incline has some coefficient of friction? Then this force would be greater than 180 newtons. And the work input and the work output would then not be equal, right? In fact, in the actual case, the work input is always greater than the work output because the effort distance, the effort force is greater than the resistive force divided by the IMA. Turns out the effort force is always equal to the resistive force divided by the AMA. Okay, so how do we figure out what the AMA is? Well, just cross multiply here. The AMA is equal to the resistive force divided by the effort force. So ideal mechanical advantage is the effort distance divided by the resistive distance. The actual mechanical advantage is the resistive force divided by the effort force. Efficiency can be calculated one of two ways. Either divide the work output by the work input, or divide the actual mechanical advantage by the ideal mechanical advantage.